Today I'll be talking about how I modeled the insulin to glucose dynamic in patients with type 1 diabetes using a system identification method. Imagine you're piloting a plane that must always remain within a range of altitude. A high altitude will cause vision problems, and a low altitude will lead to nausea and sickness. Now imagine that you paid $1 for every time you checked the altitude. If you flew daily, you may only be able to afford 5 checks per day. Additionally, an altitude check will only ever tell you what it was 15 minutes ago, and when you press on the controls to fix your altitude to within a safe range, it won't change completely for half an hour. Piloting safely would definitely become much more challenging in these conditions, and yet this is a reality of 1 in 100 Canadians living with type 1 diabetes. They must manually regulate their blood glucose levels from fatally spiking too high or too low, and the expensive glucose strips cause some patients living around the world to only be able to afford around 5 glucose measuring strips per day. Furthermore, your plane's altitude will be unpredictably affected by disturbances like severe weather. Similarly, food, sleep, stress, exercise, and the baby's needs for expecting women can affect glucose levels in unpredictable ways. And someone managing insulin manually may have to do some guesswork on how much insulin they want to take that will bring their glucose level to a somewhat safe amount. This research investigation aims to develop a closed-loop system that can automate the measurement of glucose in real time and predict, based on the current levels of insulin in the body and the disturbances mentioned, the amount of insulin to be automatically delivered every 5 minutes, keeping the blood glucose at a healthy level continuously. To create this closed-loop system, I used previously collected open-source insulin-to-glucose data from non-pregnant women with type 1 diabetes. I then extracted the raw data from 10 randomly chosen patients, giving me ample information to work with. The first set are the blood glucose measurements, and the second set are the measurements of insulin on board or IOB and a required rate per hour of insulin based on observations the system made on the patient's carbohydrates intake, exercise, and glucose level. I then averaged the required rates for each hour and added those values to the IOB to get a holistic view of how both glucose and the disturbances affect insulin levels in the body. The timings between the two were then matched, and this allows us to see a more direct relationship between glucose and insulin levels, rather than viewing glucose from the past and administering insulin that won't take into effect until 15 to 30 minutes later. This information can be used to create an algorithm that can predict future values of glucose and determine how much insulin needs to be delivered while taking into account any activities that the person is doing. Now, to actually create the control, I used a least scores approach to system identification, which is a method that builds a mathematical model of a dynamic system based on input-output experimental data and that describes the process shown here. Using the processed insulin and glucose data, I came up with around 500 to 1,000 models for each of the selected patients. Here, N is the order of the system, and D is the delay in the effect of the input. The p-values are the parameters, which can be adjusted from person to person based on their unique activities. I then summed the square of the difference between the model and the measured data. The model generated by the least squares approach with the lowest sum of errors will be used to predict the behavior of glucose and determine the required amount of insulin. The next step will be to use the best model to create a linear parameter varying design, which starts off with a process, which is the model shown in the previous slide. The parameters can vary, which affect the controller that we choose to make the system work as we want. Next, the feedback supplies the system with information about the effectiveness of the process. This can be translated to a real-life design of an automatic insulin delivery pump with actual controllers and sensors to regulate the process. The finalized model will be a stepping stone to advanced insulin delivery controls in that it automates the entire process for the patient, a feat not yet accomplished. In the grander scheme of things, we will work with medical professionals and policymakers to make this automatic insulin delivery pump approved by Health Canada and beyond. This will accelerate our goal of making diabetes management affordable and improve the delivery of home health care. Thanks for listening.